Hello everyone, welcome to my YouTube channel. So in this lecture, I will teach about another classic example of the organometallic chemistry, that is a reductive elimination. So reductive elimination is the reverse of the oxidation addition, the most often seen in higher oxidation state of the formal oxidation, because the formal oxidation state of the metal is reduced by the 2 units in this reaction. So reaction is especially efficient for intermediate oxidation states such as D8 metal, nickel 2, palladium 2, gold 3, and D6 metal like platinum 4, palladium 4, iridium 3, rhodium 3. The reactive elimination can be simultaneously by the oxidation or the photolysis. The case of photoextraction of H2 from dioxide is best known. So that means reductive in the reductivation, the metal oxidation state is decreased by 2 units and a stable molecule is eliminated from the complex. So certain groups are more easily eliminated than the others. So for example, so often proceed to write harmonization. The reaction at that involve the H such particularly fast, probably because the transition state energy is lower. The formation of relatively stable sigma bond complex along the path such complexes are known to be stable, where at least one H is eliminated. So here, from this complex, the alkane moiety is eliminated RH. From this here, the RR bond is from R is eliminated. From this, the aldehyde molecule eliminated. From this, ketone is eliminated. From this, silicon, alkyl silicon is eliminated. So in catalytic reaction, a reductive elimination is often of the last step in the catalytic cycle, and the resulting Ln fragment must be able to survive long enough to react with the substrate for the organic reaction, so the re-enter the catalytic cycle. So the elimination are the analogs to the concentrated oxide addition, in that they are believed to go by the non-polar and non-radical free-center transition state. Retention of the stoichiometry and the carbon center is a characteristic features of these groups of reactions. So that means in the reactive elimination, the retention of the stoichiometry of the carbon center is retained. So since there are several mechanisms for the oxidative addition, and the principle of the microscopic reversibility suggests that the reductive addition should show the same parity. So we only discuss the concentrated pathway here. So for the oxidative addition, there are many types of those mechanisms, like ionic, SN2 radical, concerted, and according to the reversibility principle, so this mechanism also may followed for reductive elimination. So first we will discuss for the octahedral complex. So octahedral D6 complex like platinum 4, radium 4, iridium 3, rhodium 3 tend to undergo reductive elimination readily, but with the essential loss of the ligand, we generate a 5 coordinate intermediate, a much more reactive species than the starting 6 electron complex. So when the ligand dissociation does not occur, reductive elimination can be slow, often when it is otherwise expected to be very favorable. For example, the complex with an alkyl group cis-2a hydride are rare because the reductive elimination of alkane is usually very thermodynamically favorable. A stable example of the types of the Mediterranean radium MECl with the cis H and Me, which survive settings on 100 degrees C, and ruthenium analog with weaker MPME3 bonds give the reductive elimination at 30 degrees C. So it is the PME3 turns to the high trans effect hydride ligand that is in the loss because the site is leveling. 5.8 may be more reactive because it's more readily distributed to the transition state for the reactive elimination. So it is might be expect to able reach the transition state of reactivity. It might be to expect able to gain the excess of Y type dissociation trigonal bigonal structure. So a Y structure is favored where the one pyronal ligand and C1 Cl is in this case is located in the basal position of the Y, and this structure brings two groups to the eliminated are very close to each other. The typically small r MH angle for this group may facilitate the achievement of the proposed transition state. For the after reductive elimination, a T-shape 3-point species is formed. So a reductive elimination 6 coordinated D6 species goes via then the reverse reaction, oxidation and addition to a 4 coordinated D8 species is also expected to go by the several pathway. From the rhodium ClPPSC whole 2 from the loss of PPSC to form rhodium ClPPSC whole 3 gives a oxidation addition with the hydrogen and rate of the tending faster than the 4 coordinated complex. So reversibility argument also applies to reductive elimination of alkyl halide following SN2 pathway. Applies for the oxidation direction. So iodide attacks on the coordinate methyl trans to compensate and necrophilicity displays the pitting group using the good living group. The reductive 520 interval which can even isolate in some cases can be also under constant reductive analysis of ethane if the C concentration is low. So here it's a 6 octahedral complex with first eliminate one L-type ligand to form this TBP type 5 structure. Then there is distortion, the Y type of TBP structure. This H and R group come closer to cis position in this position. Then there is the interaction between the H and R to form this intermediate. Then reductive elimination of this RH to form this 3-coordinated intermediate. Then the another molecule is L to connect to from this stable 4-coordinated species. So here for the platinum case, here first this iodide group is eliminated to form this intermediate. From here, these two methyl can also eliminated from this intermediate. Then an iodide to form this. Here the methyl bond is formed. If the and another possibility, the iodine is attached to the methyl iodide to form this intermediate. So that means the reactivity of 5-coordinated intermediate which can be isolated some case also be concentrated reactivation for ethane if the I concentration is low. So if the iodine concentration is low, then there the ethane molecule is eliminated. If iodine concentration is higher, then this is attached to the methyl to form reactive element to the methyl iodide. So other complex such as a covalent D complex, so variety of reactive elimination mechanism: dissociated, non-dissociated, and associated. Dissociative, non-dissociative, associative. Sometimes the ligand dissociate from in Rx LX2. The elimination occurs from the 3-coordinated MRLX intermediate, resulting in initial formation of uncoordinated ML metal fragment. In this case of palladium R2L2 and several gold species. In some cases, the 4-coordinated trans MRLX2 species can reductively eliminated, but usually only after the initial isomerization from these trans to cis to put 2 groups to be eliminated to next one another. So occasionally a 5th ligand associates and eliminated occurs from the 5-coordinated TBP intermediate. So this have been found for the nickel 2. Analyze that the driver and Hartwig analyze that the kinetics for the case of trans palladium AR entrosyl PPH2 where the reductive elimination of AR entrosyl takes place by a competitive dissociative and non-dissociative pathway. Palladium 2 is open slow to the eliminate, whereas because the ligand dissociation is harder, but the oxidation addition of RX to give a radium 4 intermediate can be promote the reductive elimination. Some progress has been made in understanding this mechanism in different hemota. So mechanisms are proved by the kinetics. For example, in the dissociative reductive elimination, MEME from trans palladium Me to PPH3 added to PPH3 retard the reaction in the inverse first order, suggesting the loss of the phosphine takes to give the sequential intermediate. The retardation of the mind alternatively have found due to the formation of palladium R2L3, which would have been less reactive than the palladium R2N2 itself, it can be shown by NMR. So the chelating diphosphine complex loses phosphine much less easily than do the analogs containing monooriented phosphine and undergo elimination 100 times more slowly. So the transpose complex does not eliminate ethane under the condition where the corresponding cis derivative could lose very readily. The groups of the eliminated need to be cis. Diphos locks the system to trans geometry. So here it's three example. So here for this complex and this complex, this two follows the dissociative mechanism. Here first the phosphine ligand is dissociated, then this three coordinated intermediate form, then this aryl and the pentosal group is eliminated. For the here for methyl group is eliminated. They come close to each other after. But for this case, there is a bidentate phosphine ligand. So here the dissociation of the bidentate phosphine ligand is possible. So here the reductive elimination does not occur. So in important general mechanistic experiment that is useful for this problem, the crossover experiment, a mixture of cis palladium CH3 whole 2L2 and the cis palladium CD3 is the formalized. We found that only CD3 are formed. So in that the reaction is the intramolecular. If the R groups can couple only with the same molecule of certain material. The R groups of this experiment rule out the coupling between R groups originating in the different molecule of the complex. The crossover product CDC would have been formed in the alkyl groups eliminated in a binuclear way or free methyl radicals have been formed because they are sufficient long life to migrate through the solution from one molecule to grading compound. We always need to do proper combination. For example, if CD3 is formed, we need to check whether the scrambling happens in the reaction, whether CH3 CD3 group exchange between the starting material before reductive elimination takes place, or the analytical method may be used to detect the crossover. So this can be done by isolating the starting material, start with commercial products, make sure that no CDC is present. So that means if we the cis PD palladium CSC or palladium CSC is do the reductive elimination, only the both case no crossover product is formed. Also that groups that reductive is the intramolecular process where R groups couple only within the same molecule. As so in the palladium 4 is not only very stable oxidation state, but it opens as a transition intermediate reaction. The triphos complex reacts with the CD3 to give CD3, probably caused by the unstable palladium 4 intermediate. So that is this triphos ligand react with this CD3 to form this stable palladium 4 intermediate. So dialkyl containing beta hydrogen open beta eliminated to give an alkyl hydride and the alkene before they readily eliminated. In palladium Et2PR2, the cis isomer reductively eliminated butane, but in the trans isomer, the two R groups are not properly oriented for reductive elimination. The beta elimination reductive elimination path is followed to give the ethylene and ethane. So catalytic decarbonation of aldehydes by rhodium triphos COBF4 illustrate the reductive elimination of the alkane from the octahedral lithium intermediate. So here RCHO react with the iridium CuCO to form this oxidative addition products. Then this from the carbonate is eliminated from this. Then the alkane is removed from this intermediate. So reductive elimination involving aryl groups is easier than for the alkyl. For example, the cobalt dimethyl does not lose ethane but undergoes migration interaction with added CO to give the acyl alkyl complex, which can substitute as a concern with the protonated T0 and protonated T0. So just the reaction also intramolecular. So that means The acyl groups are easily reactively eliminated from the metal complex than the alkyl. So here this is an example. Here these two Me2 group does not effectively eliminated. Here fast charge ACO molecule is eliminated from this intermediate. Then the migration instruction happened. Then after that the acyl intermediate is so from this acetal derivative. So this is also intermolecular process. The formation of a new carbon heteroatom bonds is also possible by the reactive elimination. So Goldberg found the methyl palladium acetate that forms methyl acetate in this way. And the Hartwig described a series of carbon heteroatom reactive elimination as well as the catalytic reaction that involve these steps. They are the great use in organic synthesis. So binuclear reductive elimination. Next we will discuss the binuclear reductive elimination. So we saw earlier that the binuclear version of the oxidation addition is very important for those metals that are prepared to change their oxidation state by one. So rather than the 2 units. So this is same true for the reductive elimination. So here this metal complex upon heating to from this product. So unexpectedly, the binuclear variant can even occur when the intramolecular path available carrying osmium CO4 hydride, the alkyl hydrides normally eliminated rapidly to give the alkane, but there is usual intramolecular process is not observed. CO loss because the high coordinate intermediate does not really occur because it gives only CO4. A highly unstable species is a group of 18 element is greatly prefers 5 coordinated geometry or 4 coordinated. In addition, the carbon is stronger prefers to the 18 element or 16 element configuration. So here there is no reactive elimination occur. So here osmium CO4 is not stable. So for this reason, the only on one CO is eliminated to from this 5 coordinate intermediate. The 5 coordinate intermediate is more stable than the 4 coordinate. So that's why you have the reductive elimination is does not occur. So Norton mechanism provides a bimolecular way to eliminate alkane that does not involve the 4 coordinate osmium. So the source step is a migration insertion to give the coordinately unsaturated 16 acyl complex. The resulting vacant site is filled by an osmium hydrogen bond from the second molecule of the alkyl hydride. The crossover products are seen, and so the R groups of the acyl now eliminated with the hydride to form the metal to give a binuclear complex osmium bond. Osmium bond. The hydride seems to be required for this mechanism to operate. The probable because of the hydride bridges so easily. The analysis CO parameter lacking a hydride being composed only solely to associate give this do not give an elimination by nature or otherwise. So here this is oxygen CO arranged from this migration insertion, then another molecular oxygen from this mu H complex, then upon the elimination of the RH to from this process. So here the reactive elimination occurred via this binuclear process. Don't require this node goes via osmium osmium species. So next we will discuss the sigma bond metathesis. So the apart from the oxidative addition or reductive elimination sequence, in fact, the sigma bond metathesis reaction, they are the best recognized for T0 early metals, complex such as CP2, ZrCl or tungsten Me6 because the oxidation addition is forbidden in this case. In such reaction, such complex with H2 or metal therefore cannot follow mechanism A. They do not follow this mechanism. They follow this mechanism. Here the 4 coordinated force mechanism state occur to cause this intermediate. Formation of intermediate H2 complex that is bonded to even the bigger species, the strong thermal character of any H2 species may impair the potential of to alcohol. So here, the sigma bond metathesis is possible for the D0 metal complex. So here the oxidation addition is not happened. So here this type of metal complex goes via this center transition state. For the same reason, reaction with the D0 alkyl with the acid cannot go via initial protonation of the metal because with the D0 system the metal has no lone pair. So instead of protonation, the MR bond must take place. The formation of alkane sigma bond complex then would lose alkane. For example, lead metal where both AB are normally followed, and it's hard to tell which pathway followed. Pathway A normally is assumed to operate the absence of specific evidence. So here the metal alkyl upon protonation of MR bond to form this intermediate alkyl complex, then this upon reductive elimination to form this cationic complex. So reductive in the summary, reductive elimination, the reverse of the oxidation addition decrease both the oxidation state and the coordination number by 2, and the sigma bond metathesis give the same outcome as the oxidation addition followed by the reductive elimination. In the two situations are hard to tell apart. Next, we will discuss about the oxidation coupling and reductive cleavage. So oxidation coupling, the metal induces a coupling reaction between two alkene ligands to give a metallocycle. So the formal oxidation state of the metal increased by 2 units, and the oxidation part of the name, the electron count decreased by 2, but the coordination number stay the same. So reverse reaction, which is called a reductive fragmentation, is more rarely seen. It cleaves relatively unreacted MC bond to give back to unsaturated ligand. So here, so oxidation coupling reaction, here these two alkene moieties added to form this metallocycle. So here the metal oxidation state of the metal increased by +2 unit, but the coordination of the metal does not increase, it is the same. So the alkyne undergo and the reverse one is the reductive fragmentation. So the alkyne undergo reaction more easily than do the alkenes. So alkene can be activated by electron withdrawing substituted or by the strain. Simple alkene will undergo a reaction if the metal is sufficiently pi basic. Some example is that. So here FeCO5 react with the C2H4 to form this metallocycle. This is the example of the oxidation reaction. So here this molecule they are react with the CP star to form this 5-member ring cycle complex. Then it from this complex, which is also oxidation reaction. Here this CP star Cl2 tantalum react with this alkene to form this metallocyclopropane. Here also the nickel L2 cyclopropyl metal complex react with the ethylene to form this intermediate from this product. So the intermediate on coordinated alkene are often seen, but these alkene species are more probably the intermediate precursor of the couple product. The products from the alkynes are often stable and known as the metalloless, but they can be reductively eliminated through the cyclobutadiene complex. So coupling is not limited to alkenes or alkynes. A particularly important case involves the carbenes and alkenes going to metallocyclobutane. The key step of the alkene metathesis reaction, the reverse reaction, contributes. Another example of the CC bond cleavage reaction we also see. So here we found this the carbenes MCR can couple to give this alkene R2CR2. The coupling of the isometal and carbons also be affected by reduction of 7.8 rhodium complex. So here we found this in product plus the same oxidation state ambiguity that we have seen several times before also operates here. So if the alkenes are considered to be the metallocyclopropane, the coupling reaction proceed with the formal reduction of the metal and the resemble the reductive element of two alkyl groups. In case of the reductive coupling, we show two terminal ligands because they can be coupled to complex addition. So in the summary, oxidation coupling, like the oxidative addition has oxidation state and the coordination number both increase by 2, but two new ligands are not involved, then new bonds is formed between them. So now I will discuss about some example. So first problem is, so which of the following pair in the will be more reactive toward the oxidation addition? So the factor that govern the rate of the oxidation addition is the at one of the main factor is the electron density in the metal complex. The more the electron density of the metal complex, more it will be reactive. So that means, so first here in this, so here first I will discuss some problem. So here the first problem is the which of the following is where will be more reactive toward the oxidation addition of the dihydrogen. So the here the reactivity of the metal complex will depend upon the electron density of the metal center. So we have to consider, so more the electron density on the metal center, more it will give faster oxidation addition to the dihydrogen center. So first one is the first example, the A. Between A, there is a cobalt 1 and the versus iridium 1. So between the cobalt and iridium, in decrease in the decreasing in down to the periodic table, the electronegativity of the metal is decreased. So between the cobalt and iridium, the electron density between the cobalt and iridium is less in energy, so it will give the more electron to the sigma star of the dihydrogen during the oxygen addition reaction. So for the iridium DPP, the reaction will be more favor compared to the cobalt. So next one is the, we have to consider here the metal is the same, rhodium PPSC equal to Cl, and here is the rhodium PPSC COCl. So here we have to discuss about the PPH3 versus CO. So between PPSC and CO, the PPSC is a more sigma donor ligand compared to the CO. So PPH3 will give more electron density to the metal center. So here in this case, this rhodium PPSC equal to Cl, the oxidation addition of to dihydrogen is more favorable. And for C, here is the two metal iridium versus rhodium. So here the rhodium is the more iridium is less electronegativity than the rhodium. So for iridium case, the oxidation addition will be most stable. So next for D, here we have to consider the iridium 1 versus platinum 0. So here in this case, the platinum in the zero oxidation state. So here the more metal electron density on the metal center. So for then the iridium. So here the for platinum case, the reaction will be more favored. So next question is the among the following compound will don't undergo the oxidation reaction. Here between these three compound 3 will not go the oxidative addition reaction because in the titanium it already in the plus 4 oxidation state, already is the plus 4 oxidation state. So for this complex the oxidation state higher plus 3 oxidation state is not possible to achieve because it is already T0. So for this complex 3 the oxidative addition reaction is not happening. So next question is that which of the following the iridium DBPClC or iridium DMPClC will take faster with the methyl iodide. So both here the both metal is a D8 system. So oxidation addition of the metal will occur via SN2 mechanism. So FDM1 is a more necrophilic. The which iridium will be more necrophilic. In that case, the oxidative addition with this methyl iodide will be faster. So here in case of iridium DMP CLO, because of the presence of the DMP ligand, which is more electron donating than the DBPE. So that case, metal oxidation addition will be faster. So for iridium DMPE ClCO, the oxidation addition will be faster. So next reaction, to write the reductive elimination product in the each of the following reaction. So here one. So for this one, the butane will come. The for B, it gives the CH3 C double one O I is the reactive united product, and for C here methane will from. For case 2, the D, the reactive elimination does not occur. So because here the no group has to be eliminated, and also the niobium 1 and 3 redox couple is not easily accessible. So for this case of D, no reductive elimination will happen. So next question is which of the following compound will be most likely to go under reductive elimination of ethane? Why? So here this complex C will be goes reductive elimination to from this ethane because in this complex C it is plus 4 oxidation state. So it is a highly formal oxidation state. To get stabilized to got the plus 2 oxidation state, the platinum will be the ethane will be eliminated to form this platinum 2 oxidation state. So next question is osmium CO5 and L2 OSCOC where uses an intermodulated ligand. Both undergo oxidation addition with the molecular hydrogen, with case the reaction will be faster. So between this osmium CO5 and L2CO5, both are the acylated complex. The one ligand has to be dissociated before it can go accompany the incoming ligand, the hydrogen. Since dissociation of the same ligand should be considered CO in both cases, but in this two, the osmium CO bond is stronger because the higher backbone donation. So the presence of two neutral monodentate ligand, the two will increase the electron density of osmium. So strong bonding, and it's here the CO dissociation is easily. So for osmium CO all 5, the oxygen addition will increase because the easy dissociation of the CO5 molecule. Thank you.